A research paper published 3 days ago just moved practical quantum computers from maybe by 2040 to definitely by 2027. Scientists didn't just solve quantum computing's biggest problem, they turned it into quantum computing's greatest advantage. The quantum computing industry has been promised practical applications within the next decade for the past 3 decades. Every breakthrough seemed to create new problems. Every solution introduced new complications. The timeline for useful quantum computers kept getting pushed further into the future. That just changed forever. Scientists at QuEra Computing, Harvard, and Yale have achieved something that most experts thought was impossible. They've made quantum errors work for quantum computers instead of against them. Welcome back to Click Future, where your future is a click away. Today we're breaking down the discovery that just accelerated the quantum revolution by more than a decade. To understand why this breakthrough is so revolutionary, you need to understand the fundamental paradox that has trapped quantum computing for 3 decades. Quantum computers get their power from qubits that can exist in multiple states simultaneously. Qubits are incredibly fragile. They lose their quantum properties when disturbed by heat, vibration, or electromagnetic interference. When this happens, your quantum computation fails. This will be one of the limits on scaling quantum computing. The costs and complexities are challenging top engineers and scientists across the globe. Here's the cruel catch-22. The more qubits you add to make your quantum computer more powerful, the more opportunities there are for errors. It's like trying to build a house of cards in an earthquake. The bigger you try to make it, the more likely it is to collapse. Traditional quantum error correction tries to solve this by using multiple physical qubits to protect each logical qubit. But this approach requires hundreds or thousands of physical qubits for each logical qubit. It's like hiring 1,000 bodyguards to protect one person. Technically, it works, but it's so inefficient that it makes practical quantum computers nearly impossible to build. Current quantum computers have error rates of 0.1 to 1% per operation. When you're performing millions of operations, those errors compound exponentially. By the time you finish your calculation, the result is completely unreliable. This is why every quantum computing timeline has been wrong. Every time scientists solved one aspect of the error problem, the scaling requirements made the overall problem worse. The more powerful quantum computers became, the more impossible they became to build. Mohammed Abou-Bey, a Harvard postdoctoral fellow working on the breakthrough, explained the severity. Atomic loss is a major bottleneck for this system. Without solving this, there's nowhere to go. Everything changed when the QuEra, Harvard, and Yale teams stopped trying to prevent quantum errors and started trying to use them. Their breakthrough, called Algorithmic Fault Tolerance, or AFT, doesn't protect qubits from errors. It restructures quantum algorithms so they can detect and correct errors while the computation is still running. Instead of stopping the computation to fix problems, the computation fixes itself. Think of it this way. Traditional error correction is like having a spell checker that only works after you've finished writing. AFT is like having a spell checker that fixes your mistakes as you type without interrupting your flow of thought. Dr. Henjin Zhou, the lead researcher, described it as transversal algorithmic fault tolerance. The quantum algorithm itself becomes fault tolerant rather than just the hardware. The computation and the error correction become the same process. Results are staggering. AFT reduces the time and computational resources needed for error correction by 10 to 100 times, depending on the algorithm. That's not an incremental improvement, that's a complete paradigm shift. Here's what makes this even more revolutionary. AFT works particularly well with neutral atom quantum computers, which have advantages that other quantum computing approaches don't. Neutral atom quantum computers use individual atoms as qubits, held in place by precisely controlled lasers. Unlike superconducting quantum computers that need to be cooled to near absolute zero, neutral atoms can operate at room temperature. More importantly, neutral atoms can be moved around and reconfigured in real time. Any atom can interact with any other atom, which means they aren't limited by fixed wiring like other quantum computers. Yuval Boger, Chief Commercial Officer at QuEra, explained why this matters. In neutral atom systems, any atom can be moved to interact with any other, which means they aren't limited by fixed wiring like superconducting qubits are. This all-to-all flexibility is a natural fit for fault-tolerant schemes. The combination of AFT with neutral atom hardware creates what researchers are calling a perfect storm for practical quantum computing. You get the error correction efficiency of AFT with the flexibility and simplicity of neutral atoms. So what does this mean for the timeline of practical quantum applications? According to Yuval Boger, this moves the timeline forward significantly. While we're not at full fault-tolerant systems yet, this result shows that the enormous overhead once assumed is not inevitable. Let's put this in concrete terms. Before AFT, experts predicted that practical fault-tolerant quantum computers wouldn't arrive until 2040 or later. The overhead requirements for traditional error correction were simply too enormous. With AFT, that timeline has been compressed to 2027 to 2030. We're talking about accelerating practical quantum computing by more than a decade. This acceleration has massive implications across industries. Pharmaceutical companies planning quantum drug discovery projects for the 2040s could now move those timelines up to the late 2020s. Financial institutions that dismissed quantum computing as too far in the future are now seriously evaluating quantum algorithms for portfolio optimization and risk analysis. Even artificial intelligence could be revolutionized much sooner than expected. Quantum machine learning algorithms that were theoretical curiosities could become practical tools within 5 years. Dr. Peter Zoller, a quantum physicist at the University of Innsbruck, who wasn't involved in the research, called AFT a game changer for the field. He noted that reducing error correction overhead by 2 orders of magnitude could accelerate practical quantum computing by at least a decade. The breakthrough also reshapes the competitive landscape. Companies that have been focusing on superconducting qubits, like IBM and Google, might find themselves at a disadvantage compared to neutral atom approaches. The European Union recently announced a €1 billion investment in neutral atom quantum computing research. The U.S. Department of Energy is funding multiple neutral atom projects. Even China is pivoting resources toward neutral atoms. QuEra's breakthrough with AFT could give them a significant competitive advantage, but it also provides a roadmap that other companies can follow. According to QuEra's roadmap, they expect to demonstrate AFT on their quantum computers within the next year. Hardware tests are planned for 2026, with practical applications potentially coming online by 2027. The implications go beyond just faster timelines. AFT represents a fundamental shift in how we think about quantum computing. Instead of trying to build perfect hardware, we're learning to build perfect algorithms that can work with imperfect hardware. This philosophical shift could apply to other quantum technologies as well. Quantum communication, quantum sensing, and quantum simulation could all benefit from algorithmic approaches to fault tolerance. The acceleration also means that solutions to humanity's biggest challenges could arrive much sooner than expected. Climate change, energy storage, carbon capture, fusion power. All of these involve quantum mechanical processes that could be accelerated through solutions found with quantum computers. Materials science could be revolutionized by 2030 instead of 2040. New medicines could be discovered in months instead of decades. Financial systems could become more stable and efficient years ahead of schedule. There's also a competitive angle that most people are missing. The countries and companies that successfully implement AFT first will have massive advantages in science, technology, and economic development. The next few years are critical. Organizations that can successfully scale AFT to larger quantum systems will dominate their industries. Those that can't might find themselves permanently behind. The AFT breakthrough represents more than just a technical achievement. It represents the moment when quantum computing's timeline shifted from someday to soon. For 3 decades, quantum computing has been trapped by its own paradoxes. More power meant more errors. Better performance required impossible overhead. Practical applications remained perpetually out of reach. That era just ended. Scientists have turned quantum computing's greatest weakness into its greatest strength. The quantum future isn't coming in 2040, it's coming in 2027. What do you think? Are we ready for practical quantum computers to arrive a decade early? And which applications are you most excited to see accelerated? Let me know in the comments below. If this timeline shift changes how you think about the quantum future, make sure to subscribe to Click Future for more analysis of breakthrough science. Hit that notification bell so you never miss the developments that are reshaping our technological timeline. Your future is a click away, and thanks to algorithmic fault tolerance, that future just got a lot closer. Next, we'll explore the $100 billion quantum race heating up between IBM, Google, and Microsoft, and make a prediction about who will win that race.